I'd like to introduce you to the world of industrial control systems, or ICS. Inside an operating facility, ICS refers to the systems and components that actually control mechanized operations. Claroty's continuous threat detection, or CTD solution, is specifically designed to operate as part of these ICS or OT environments, and in this module, we'll be learning the basics. For example, the technology you'll see in this sector. What is an ICS network? And what's different about these networks, and why should we care about those differences? In context of OT, you will hear frequent references to the Purdue model. This is a model used in OT networks to distinguish between devices used in the industrial control system and devices that are part of the background architecture, and to classify the role of each device as part of the overall network. This model uses what is called the Purdue Enterprise Reference Architecture to describe the distribution of network devices within OT networks. To start at the bottom, Level 0 includes the plant's field-level devices like valves, motors, and similar. Level 1 covers control devices like PLCs and HMIs. Level 2 covers process-level devices higher up in the hierarchy, such as engineering workstations and historians. In the following slides, we'll go into more detail on each level that relates to OT and process control. Level 0, which is the bottom layer of the Purdue model, covers field-level devices like the small selection shown here, with each field device being responsible for a specific set of action or actions within the process environment. Each field device is connected to an I/O card that maps the input and output signals from the field device to memory addresses. The field devices are controlled by Level 1 devices such as PLCs and remote terminal units, or RTUs. All communication between the controlling device and the field device is done using electrical signals. Moving up the Purdue model to Level 1, which is the control network, we start dealing with programmable logic controllers. These are ruggedized digital computers that are optimized for real-time processes and are used to automate electromechanical processes like the control of machinery on factory assembly lines. A PLC's main job is to read information and control I/O devices to achieve the full capability of the machine being controlled. PLCs communicate with field devices using proprietary protocols that are usually unique to the PLC manufacturer. This is a major problem from a security point of view, because if a PLC is compromised due to malicious activity or human error, and you don't have the tools to understand the communication protocols, protecting your network becomes impossible. Let's take a quick detour into the PLC's I/O cards. Each field device is connected to an I/O card within the PLC that maps the input signals into and output signals coming from the field device to memory addresses. The PLC runs a program that checks the current status of the memory addresses, and based on the program's logic, the PLC then changes the values at other memory addresses. The I/O card then translates the later memory address values to electrical signals, which are then transmitted to field devices which do the physical tasks required. We can see a couple of input-output flows in the examples shown on this slide. Moving up the Purdue model to Level 2, which is the process network, we start dealing with human-machine interfaces, or HMIs. These are control units that allow plant operators to directly control PLCs. Like PLCs, HMIs communicate using protocols that are unique to the company that manufactures the HMI. Communication with HMIs is usually two-way. The HMI reads information like device status, I/O state, control data like temperature readings and PLC errors, and can issue commands that trigger predefined operations like starting and stopping field devices. In that respect, a single HMI is usually configured to control a single PLC. HMIs are usually also able to do data acquisition from PLCs. Moving up the Purdue model to Level 3, which is the operations network, we start dealing with engineering workstations. These are typically Windows-based computers with installed software that allow a human operator to manipulate the logic of a PLC. In that respect, the difference between an HMI and an engineering workstation is that engineering workstations are used to perform lower-level changes on the PLC, like changing parameters, firmware upgrades, and operational programming. Protection starts to become really important at this stage, because if an engineering workstation with extensive access privileges is compromised, an attacker can make low-level changes to PLCs. Without specialized tools, changes done at this level can be very hard to identify as a threat. For example, an attacker could use an engineering workstation to program an electric motor to operate at a higher speed, but could also program the HMI connected to the motor to show a normal operating speed. Remaining with Level 3 and the operations network, another system we'll need to become familiar with is SCADA, or Supervisory Control and Data Acquisition. This is a system that uses coded signals over communication channels to remotely control equipment. That function can also be combined with a data acquisition function. That means the system can also capture, display, and if needed, log information about the status of the remote equipment. As a rule, a single SCADA system is used to control and acquire data from multiple PLCs. So SCADA systems can also be said to have a data aggregation function. We'll finish this module with some of the common industrial protocols used in ICS operations. What you see here is not an extensive list of every industrial protocol used out there, but it will help to know that all the protocols you see here, and many more, are all supported by Claroty. The full list of Claroty-supported ICS protocols is available on request, but a list like this gives you, first of all, an indication of just how many different protocols are out there, and second, an indication of just how different the operating conventions are in the OT sector compared to the equivalent conventions in IT. One of the big challenges in the OT environment is the sheer number of things that have to be worried about. So now you have a better understanding of what the world of industrial control systems is like, and also some of the ways you can expect the OT environment to behave differently from IT. These differences are why specific cybersecurity solutions are needed to secure OT networks, instead of just using standard IT solutions. As you've seen, there are many different protocols, and the operation of an OT environment is very different to that in IT. This is the environment that Claroty's continuous threat detection and secure remote access solutions were built for. With that, we conclude the module, and thank you for your time.